Hello, folks. Welcome to Rational Science. We have a great day today. We're going to be talking about dark matter, and we're going to find out that the mathematicians are full of dark matter. Anyways, we had people put a lot of comments regarding the moon. Had a lot of moonies, and one of the things that really surprised me is the number of people that do not believe that we landed on the moon. And I don't know if it's just the new generation, or that did not experience what happened in 1969, or is it people that don't like government telling them so many lies, and so they stopped believing in everything. They threw away the baby together with the wash water. I don't know what the issue is, but in my mind, I thought it was maybe, I don't know, 1 or 2% people out there that did not believe that we went to the moon. Turns out that I had to revise my estimate. I think maybe there's anywhere from 10 to 20% people out there that probably do not believe that humans went to the moon. And that was kind of surprising for me. Anyways, this is what I'm going to be addressing first half, because there were so many issues with the moon, I don't think I can touch anything else. And here, yeah, we're going to deal with the moonies again, okay? Okay, so let's find out what these people are all about. Okay, and there are several issues involving the moon as well that people commented on. So here's the first fellow. He said, the moon doesn't orbit around the Earth. The moon doesn't around the Earth. And this is like, someone pointing at white and saying, that's black. And you look again, just in case your eyes failed you. You say, no, that's white. And the guy's saying, no, you're staring at black. I mean, here you see, he points to a site in YouTube. I go there, find out what it's all about. Maybe they've got a different kind of moon or something. I don't know, maybe he's talking about a moon of another planet, And what you see is first that it's our planet, it's our moon, I guess. That's what they seem to show there, right? That's what they talk about. And you can see the first error there is that, the moon goes at the same rate as the Earth. Okay, and that's a big problem because the Earth turns on its axis every 24 hours, whereas the moon, takes 27 days to go around, the Earth. So the speeds there are a little different. That's the first issue. And then the other issue is whether the moon goes around the Earth. Let me repeat that because you may have not understood what this guy said. The moon goes around the Earth. Does it go around the Earth or not? Well, for this, we got to look at the word around. This guy doesn't seem to know English. Maybe he's, from Mexico or someplace, It says, if you look up the word around, it says, in a circle, ring, or the like, so as to surround a person, group, thing, etc. Yeah, it looks like that moon is surrounding all around the Earth, okay, on all sides, which is what you see there, and in all directions from a center or point of reference. So yeah, the moon goes around the Earth. Sorry to tell you that, but I guess, I don't know if people want to sound cute or what. So the first thing is the moon does go around the Earth. It goes all around. In fact, every part of the Earth, it doesn't matter where you're at. You could be in Africa, you could be in China, in the Americas. You should be able to see the moon at some point in time, during the month. And that's because the moon goes all around the Earth. So yeah, the moon does go around the Earth. I don't know how else to tell you that, but yeah, some people say that white is black and they're staring at white. Okay, and that's essentially what we've got here. And then the other issue again is that the moon is not, or the whole orbit is not illustrated property. Okay, it's not illustrated property. What's wrong? Well, what's wrong is that, again, the moon always shows us the same face, but the Earth spins a lot faster than the moon goes around the Earth. And so, every part of the Earth has a chance to see the one side of the moon. Okay, and so yeah, I don't know what these people are thinking. Maybe they want to sound cute. The guy who made that video has no clue about anything. And what's interesting, they get thousands of hits, and people go, ah, oh, ooh, and then they bring it here. Jesus Christ. Okay, another fellow says, another Moonie. Okay, we got a lot of Moonies here. Moon takes 27 days to rotate around its axis according to the model. You did not do your homework on this. Moi. You believe this like a religion, it seems. Well, I don't know. Maybe he's a flat earther. He doesn't believe that the moon, goes, around the Earth every 27 days. It does. That's one issue. Maybe that he was referring to that. Maybe he was referring to spin. Maybe he was saying, the moon does indeed spin, but the spin is equal to its orbit. Absolute nonsense. Absolute nonsense. So let's clarify that for all the, mental cases that we have out there. Let's clarify that. Kill that once and for all. The moon does not spin. Okay. Here I have a pencil. Okay. We have a pencil. Let's see if you can follow it. Let's see if you have the intelligence to follow this. Let's color code the pencil. We'll put red on this side and blue on this side. Okay? So we're going to have red on this side. I should have done that, but I think you can follow it. Red on this side, blue on this side. Does the Earth spin? Yes, it does. And let me tell you why. Because if this is the axis of the Earth going right through, North Pole to the South Pole, right? Well, Africa will be looking at red at some point, and at some point it'll be looking at blue because it twirls around, the whole Earth twirls around. Africa at some point will face red, at some point it will face from this side, face blue because it's twirling around. If we do the same thing with the moon, okay, we put an axis right through the center of the moon. Anywhere you want, okay? I don't care because it doesn't matter in the case of the moon. Well, the Earth, the moon might go around the Earth, always showing the same face. But any point on the surface of the moon, the one that's facing red will always face red, more or less, because it wobbles a little bit, right? But it'll face red, and any other point will face blue. And no matter what, the moon can stand on its head if it wants. It's always going to show a mountain, a given mountain, a hill, whatever, to the red. And the other one's going to show it to blue because it does not spin. Let me tell you what spinning looks like, okay? I know you guys see, this is what happens when you skip kindergarten, okay, in elementary school, okay? This is what a spin looks like, okay? And again, the reason it spins is that if that axis, if we could make it remain fixed, okay, so that we could gauge whether it's spinning or not, any point on the surface of that top is going to change locations with respect to some place on the axis. If we could color code it, have red on one side, blue on the other side, whatever edge that you want to pick on that top, we'll sometimes see red and sometimes see blue. That's not the case with the moon. The moon does not spin. Okay? And only people who don't understand that will say that, oh, the moon doesn't spin, spins, or equals its rotation or whatever. Yeah, these people think they're cute and they're trying to sound intelligent. All they do is just show their ignorance. Haven't even done the research on it. No, the moon does not spin, okay, in any way, shape, or form of the word spin. Okay, the fact that it rotates or revolves or orbits the Earth around the Earth, right? It does go around the Earth. While doing so, it does not spin with respect to an imaginary axis that it could have, that you could put in there by hand. Okay, moving on. Here we have more Moonies to deal with today. A bunch of Moonies. We didn't go to the moon, says one guy. The Earth is a sphere. Atoms are not orbiting balls. Well, they look like orbiting balls to me. I mean, that's how everybody puts atoms, with all these little beads moving around. And, the issue here is that people say what it ain't. Don't tell me what it ain't. Tell me what is. That's where you show a little intelligence. But it says atoms are not orbiting beads. Okay, they're not or balls or whatever. If they're not orbiting balls, tell me what it is. Please draw a picture or put in a link and say, look, here's the true, genuine atom. Because when you look at the atom, anywhere you want to look at it, that's what you see. You see orbiting beads. So don't tell me that the atom is not orbiting beads, because that's what everybody uses out there. In fact, quantum mechanics would not be able to explain electricity the way it does today unless the atom consisted of orbiting beads, because they're going to take one of these little beads called an electron, and they're going to move it around from atom to atom, sometimes without atoms, as we discussed a couple lectures ago. So yeah, the atom that is used by all of quantum mechanics has not changed since the day Niels Bohr and Ernst Rutherford came up with it, which is the planetary model. Okay? That's the atom that's used for ionization, that's the atom that's used for electricity, and that's the atom that's denied at the end of the conference, saying, well, that's not our true atom. And that's what this person did here. It says, that's not the atom. Okay, then what is? Okay, and yeah, he says you didn't go to the moon. Yeah, I guess, statements. No justification, no argument, just, we didn't. I don't believe it. Okay. Here's another fellow, he says, proof, oh, sorry, Bill, one of your worst vids ever. Okay. Insane ramblings and gibberish from you to support such an obvious NASA fraud. NASA have lost all tapes of moon landings and proof. Oops. Well, I don't know about that. I mean, he thinks maybe it was all filmed in Hollywood or something. Why would NASA, what would be the motive for NASA for 60 years? Because if it's one deal like, JFK's death, it's easy to argue that this was done by Johnson, J. Edgar, and Allen Dulles. 9/11, yeah, what's his name? George Bush's crew, no problem. Why? Because it was one day, it was 1 minute, it was a short time. And then immediately goes into history. And then all you can do is rely on maybe some pictures that someone took out there, etc. Here we're talking about 60 years of NASA. 60 years, at least. I mean, I'm sure it's right after the World War I. Same for the Russians. And so these guys have been sending rockets out there, okay, for 60 years. And you're telling me that all that is fake. There were no rockets. We've never gone into space, okay? And we've never orbited the Earth. We haven't put a lab out there in the sky, sky lab rolling around the Earth. That not only hasn't happened, but is not happening. That's all fake. And this is very easy to kill your ignorance. I mean, kill your ignorance, okay? And what I'm saying is, go to Florida, the next launch, take your camera, your high-powered camera, right? Take your telescope and film the damn rocket go into space. Okay, you can see it go until it's gone. And so don't come with nonsense, with idiocy, saying that we haven't gone to space. For example, some people, because there are different levels. Some people say we haven't gone to the moon. Others say we haven't gone into space. Other people say we don't even have satellites out there, that it's all done, underground. I mean, these people are so ignorant. And it's more than ignorance. It's something, if they want to kill their ignorance, there are ways of showing that. I mean, the time they spend arguing, they could go to, again, Florida and just film it. I mean, or get a friend to do it over there. Call the flat earthers over there in Florida and say, please, flat earthers, the Flat Earth Society, would you be so kind as to film the rocket go to space next time around? I mean, you have to be a total ignoramus. And so now is homework. I want you to look at the mirror, okay, this coming Thursday or Friday, okay, look at the mirror, and 10 times say to the guy in the mirror, you're an ignoramus. 5 times at least. 10 times. Always looking at Mecca, okay? My God. Another flat earther. Okay, here we have your Moonies, flat earthers. Impossible for something to be flat with hills, mountains, depressions, valleys, elevations. What I don't observe is over half my nearest mountain under curvature isn't hidden. Uh, I can see over 100 miles away a mountain from bottom to top. Anything can be round. My table is round. So, see, these people want to prove flatness or curvature by saying, well, when I look at the highway, it looks pretty straight to me. Yeah, no kidding. One of the issues there is when they built the Siberian Railroad, probably the longest thing we've got on Earth. They constructed in the 19th century, and it went, from one side of Russia to the other side of Russia. And of course, it went into hills and valleys because, as far as I know, no country is evenly flat. And then you have the curvature of the Earth. And, Russia has a significant portion of the curvature on Earth. So not only does it go, over mountains and hills, but it goes over a curvature that has mountains and hills. And maybe you should contact those architects and engineers who built the Trans-Siberian Railroad, and they can tell you all the problems they ended up having because the Earth is not so flat. And again, not only because of hills and valleys, okay, but because the Earth is curved, okay? And so, for flat earthers, what can I tell you? They proved that the Earth was round. What was it, in the days of the Greek? And yeah, you don't have to believe that proof because, again, we don't have proofs in science. But here you have a good argument put forth by the Greeks of why the Earth was round, and you should read up on that, Okay, and here's another fellow. He says, it is so easy to get to and from the moon with technology from the 60s. Then today, for every nation that has developed space technology, they would have their own lunar base or an international complex like that shack that orbit around the Earth. Okay, so if it's so easy, why don't we have lunar bases? Why isn't everybody on the moon? And he says, I could come and go from the moon for my Christmas or summer holidays, do lots of selfie and look at the blue pearl from the window of the Luna Hotel. What can I tell these people? There was no reason to ever go to the moon in the first place, and there is no reason to go to it now. Now, why did they go to the moon? Well, they went there not so much for the moon, because they realized that it was a bunch of rocks. They could maybe find something on the moon, maybe a little bug crawling that they never thought about. Yeah, they could have had some surprise, okay? But the issue was to develop technology. That was the primary reason. Other than that, going to the moon saying, we did it, we made it to the moon. And again, the hope, which is still in NASA and all these other space agencies, is that someday we will be colonizing space. Especially, planets first, maybe the moon, right, or other moons, and then eventually, the nearest star system from there on. This is the mentality that all space agencies have, and that's what keeps them breathing, because they think that we're really going to go out there, maybe even meet the Klingons, coming our way. Never going to happen. It's never going to happen. I mean, we're not going to colonize the moon, we're not going to colonize Mars, and that's why, there are no more flights to the moon. First of all, they're very, very expensive. Second, the return on investment is nil. The best you can hope for is maybe create a tourism to go to the moon. Some people with lots of money will say, oh, I'll pay for a trip, I want to go to the moon. Okay, so they go to the moon, they go for a week or 2 weeks or whatever, and then come back, or maybe less, I don't know. Some people would be glad just to go into space. Others would like to go to the moon. Sure, no problem there. But it's just for that. There's going to be no colony on the moon. Okay, and these people don't understand the logistics of going to the moon in the sense of supplying the moon. You put a base there, you got to supply it, quite often. You got to take water over there. You got to take food over there. What are they going to do? Grow potatoes? And you might say, well, they can build one of these places where like inside with all the lamps and so on, growing all kinds of food in there. It's never going to happen. You know the monster it is just to take all that stuff out there for a small operation. What for? Are we going to evacuate the Earth and go to the moon, which is a smaller rock? Okay, first of all, smaller, much smaller. No gravity. That means you have to produce your own gravity. Anything can go wrong. You might lose pressure, loss of life. The whole experiment goes to nothing. What for? Who would go to the moon to live on the moon forever? Is that what these people are thinking? Who would go to Mars? For what? And who would pay you to go to Mars? So I pay for you to go to Mars and I never see you again. So why did I pay for your trip to Mars, right? Because you're going to stay in Mars, I'm going to stay on Earth, and you're not going to have commerce with the Earth because whatever you bring over, I'm sure I can produce a lot cheaper here. Why would I pay for your trip in the first place? Why would I contribute, from the earthly treasury to send you to Mars? People are they're not thinking. They're not using their brains. That's what it amounts to. And then they have contradictions because a lot of these people, on the one hand, don't believe we went to the moon because man can't be in outer space, et cetera, et cetera, et cetera, and then says, oh, someday we're going to go to Mars. Well, I thought you said that we can't live in space, that we can't go into space because we will be zapped by the sun, by, the radiation, or maybe our suits are no good, we can't live out there in space, and then you're talking about going to Mars? These people live with so many contradictions, it's just unbelievable. Okay, so here we have another Mooney. We humans never moon landing. However, we sent a lot of machinery there. Oh, okay, so that wasn't Neil Armstrong on the moon. That was a robot. Sorry, my eyesight is failing me. Maybe I missed the robot. I thought it was Neil Armstrong jumping on the moon. Okay. The first one recorded is the Russian spacecraft, etc., 1959. 60 years later, again, we humans send robots, probes, rovers. So if we send all this stuff up there, if we can send robots or whatever to the moon, why can't we send a human to the moon? You gotta answer that question, because if you think that, we sent all this, all these mechanical devices out there, to use that term, robots, etc., androids maybe, I don't know, then why can't we send a human? You're talking about, some trip, what is it, slightly over a light second to go to the moon. So if we took that much trouble to send all these things to the moon, why can't we send a human? And again, these people live with all these contradictions. They never resolve them. Okay, here's another fellow. He says, you literally contradict yourself with your point regarding mathematicians. It's the mathematicians that support moon landing, but provide no physical evidence. The guy's looking for proof. He's looking for proof, or I want you to prove to me that we went to the moon. Well, like I said last time, I can't prove to you that we went to the moon, because the only way I'm going to prove, if I show you a movie, you're going to say that was made in Hollywood. Okay, great. So what am I supposed to do to prove to you, what evidence can I present that we went to the moon? I give you a moon rock. You say, well, that was taken out of Africa, out of the mines or out there in South Africa or whatever. So what can I show you? What kind of evidence do you want to prove to you that we went to the moon? And the only way I can prove to him is taking him back in time to 1969 through the fourth dimension, of course. And we go there, I take him by the hand to the moon and say, look, see, that's Neil Armstrong there and that's Buzz, Is that the way I'm supposed to do it? So, Jesus Christ. And fellow says, this is something that mankind likely will never do. We'll never go to the moon, to space, to Mars, to anything like that. It's unbelievable. And we will never achieve flight, certain speeds, etc. What's the issue? The issue is, he's saying that it's a mathematician that, vouch for this theory, this hoax that we went to the moon. And all I can tell him is that, the mathematicians have nothing to do with this. The fact that this is run by NASA, that's not an issue of mathematics or even of mathematical physics. This has to do with really with technology. Whether we have the technology to go to the moon, whether we have rockets that can go out into space, it's got to do with that. It's got nothing to do really with mathematics, or with mathematical physics. So, again, these people are pulling at straws here to see if they can win an argument or something. I don't know what they're into. And here's another fellow that says, it looks like you have to do a lot more research on this subject. Oh, okay. Yeah, maybe I do. Start small, okay. Start very little, okay. May I suggest the pictures? Okay, pictures. Now that's good for evidence, right? Pictures. Okay, so I'm sure they're all hoaxes, okay. Look at the Hasselblad, which is a camera, right, that took the pictures on the surface of the moon. Okay, what about it? I challenge you to find the blueprints on the modifications for the heat, cold, radiation, and pressure. I mean, all these people come up with all these arguments about the photograph is wrong or the photograph is right, or the blueprints of the camera. Jesus Christ, these people, they have mental problems. I think they do have actually mental problems. Okay, and here we have another fella talking about vacuum also and pressure. That's one thing that gets people, riled up as far as the moon landings. Very important subject with them. So we can't withstand the pressure or the vacuum. And here is this fellow says, people in the flexible, bendable suits, magically withstanding ultra high space vacuum. Please. Yeah, they don't believe that we can withstand vacuum. And that's, for me, incredible that they have these notions and they say, well, we can't do it and that's it. I don't believe it. And that's where it stops for them. No research, no thinking, no nothing. And so let's go through that, because that's a big one for a lot of these people, moonies, who don't believe we went to the moon. They say, we can't withstand the vacuum, etc., etc., etc. Okay, so here it is. Let's start here. We have the people who go underwater, way deep. And that was one of the first suits, the one on the upper left there. And what is it? You see that it's very rudimentary. And this was in the 1930s. And they would drop the guy all the way to the bottom. He was under a lot of pressure in the water. Remember, the water has a lot more pressure here down there than up here in the air. And so the guy was under a lot of pressure, but the suit was built because they already calculated how much pressure the guy would need, or anti-pressure, right? How much resistance he would need against all that water pressure at certain depths in the ocean or the sea, wherever he was sent. And so they already calculated, they built that into the suit, and the guy could withstand the pressure. And today we have better suits, and much, they've studied all this stuff in a lot more detail, so the technology is there. Technology to go under the water is there, okay? And you may not believe it. You say, well, I don't believe that we can go underwater. Well, this is something that you can kill your ignorance, okay? You don't have to believe. You don't have to take my word for it, okay? Okay. And so that's the first step, okay? So as far as I know, we can go underwater, under very high pressure. Can we go into the vacuum, like space? Can we go to 10 to the minus 6 torr, 10 to the minus 7, 8, minus 11, minus 12? Yes, we can, okay? The answer is yes. Okay, so here let's go through this. Here we have a human. Okay, and it turns out that you are already protected from vacuum of space. 10 to the minus 11 torr out there in the black part, right? You're already protected by air, magical air. I mean, if we took all that air out, you would be exposed to the vacuum. We would all die. That's how simple it is. Okay, so right now you are being protected from the vacuum, from the pure vacuum of space by all this air stuff, this gas that surrounds our planet. Okay, so keep that in mind. You know, if you go out there, you have a problem because you have no protection. But right now you do have protection here on Earth. And all we have is just that, the pressure from the air to which we are used to, right? And so we're protected from all this vacuum simply by that air, natural protection. Okay. Okay. Now here's you. Okay, and that's you in your suit. Okay, and you're out in space, and you have your space suit, and you say, well, does that really protect me? Okay, well, here's you inside your suit. Okay, that's more or less what you would look like. Okay, probably. Okay, something like that. And when you go in there, what does a suit have in there? Well, it has some kind of protection. Okay, it has some kind of protection. It has already the built-in pressure that you need to survive, no different than when you are here on Earth. In other words, you have something in there between the skin of your suit and your skin that already has the desired pressure, no differently than the people who go underwater and have protection against the pressure. This is no different. Okay, so you already have something in your suit that protects you in that way. Why would you not accept this? This is what blows my mind, that we already have protection against space from the air that surrounds us every moment. The closer you are to Earth, the more pressure there is. The higher you go, air is less dense, and the more you go up there, the less pressure you get, until you finally get into outer space, where you get into the minus 10, minus 11, minus 12 torr range. And of course, you cannot withstand that without a suit. Okay, so the question is, how do you protect against that? Well, just like you protect yourself underwater by building, an anti-pressure suit, when you go into outer space, you build an anti-vacuum suit. Okay, and that's what they do, and that's what they test over there in the Ohio testing center that I talked about the other day. And so I have no idea what these people are talking about when they say that we cannot withstand a vacuum out there. Well, maybe it's the vacuum between your ears that you can't withstand. That's the problem. That's the real problem. Okay, another fellow says here, he says, costs of a lot of money, it has no meaning. Money is no object. Going to Mars, going to Jupiter, we have all the money in the world for these things. Money is no object. If we have the concept of the union of humans for a common goal, oh yeah. We have a communist on board, maybe an anarchist, okay? As happened for the conquest of space in the 70s by the USA and the USSR. Yeah, I mean, if they were all friends, right? He's saying, if we're all friends, the Chinese, the Russians, the Americans, everybody was friendly, right? Instead of fighting, using all that money to fight each other, what we could do is, pool that money and go out into space. And maybe the counter argument is that if we have no one to fight against, maybe Mother Nature does want competition, because if we have monopoly, one world government, maybe our economy goes to hell. Ever think of that? Anyways, so just imagine for a moment if all the military efforts of USA, Russia, China, etc., right, coincided with a single goal. Yeah, we're going to spend all that we have. Well, no, we have no one to fight against anymore. We don't have any more armies. We don't need them because there's no one against which to fight. We're all friendly now. We all kiss and make up. We're all brothers. So now we have all this money left over that we don't have to spend on military and all that stuff, and we can spend it on dummy stuff like going into space. For what? For going to the moon? Maybe to Mars? To do what? I don't understand these guys. These guys think they're going to go to the moon, put a little cabin there, log cabin, maybe have what, Christmas on the moon, maybe in the sea, like the other guy with the hammock. If it were possible for humans to go to the moon, if it were possible, how long would it take us humans to build something there? And how easy would it be to keep the facilities there? Yeah, how soon would it be? And how much would it take to feed and clothe and send water up there and all the besides the construction, you would constantly have to send all kinds of stuff to build something on the moon. Maybe you need several trips. And yeah, this guy apparently has more money than Bill Gates. He says, well, I can do it. Money's no object. Okay, well, some people have more money and they spend it in whatever they want, I guess. And then it says, what does Mars and Pluto have to do with it? Okay, humanity is unable to go beyond low orbit, and you announce travel to Pluto. Well, yeah, I mean, I'm saying that we could go to the moon, to any of the moons of any of the planets. We could go to some of the smaller planets like Pluto, maybe even Mercury or Venus. I don't know. We could probably get there. I don't know if we can come back. Well, we would certainly get there. I think we have the technology to get to Pluto if we want. Now, can we do it? I mean, they did send probes to Pluto and beyond. For those of you who believe that, okay, yeah. And it doesn't mean a human has to go. We can send a robot and it takes pictures, whatever, and we've done that. And what we found is that there's a bunch, what we know already from Earth, that Jupiter is a gaseous planet, so is Saturn, Neptune, Uranus, and that the rocky planet known as Pluto, some people say it's not a planet, and Mercury and Mars, they're just rocks. So we know that now. And why are we going to go there? Again, put a station, evacuate the Earth, colonize, conquer the Martians, look for life? Maybe. Yeah, sure. You are so limited. Yeah, I've got problems, okay? You say that the only purpose for humanity to go to Mars is to say, yes, we have been there. Yeah, exactly. That's it. That's the only purpose of going to Mars. Now, the people at NASA and all these other space agencies, they have goals. They say, maybe we can get to Mars. It would be nice to put a colony there, or maybe a station first and then gradually build on it and build a city. And, they have all these dreams. They have all these dreams. And there's no atmosphere that we can live on in Mars, so we would have to take our atmosphere with us for quite a while, Who was it? Carl Sagan said that it would take over 100,000 years to terraform Mars, the gas, right? To be able to live within Mars. And again, Mars would hold a lot less air, gas, pressure, gravity, etc., 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 than here on Earth. Why would we go to Mars? Are we crowded here on Earth? Are you feeling elbow room problems? Maybe on the bus or whatever. You got claustrophobia. What the hell, Bill? Be more open-minded. Consult, inform yourself, study. Well, what can I say? What this guy said the other day, I'm old school. I just believe that man went to the moon and back, and that's it. And all these people are new school, I guess, and they believe not only that we haven't gone to the moon or to Mars, right, in any way, shape, or form. Some of them believe that we haven't gone into space. Some of them believe there are not even satellites out there, but that someday we're going to go to the stars and maybe even to the center of the galaxy. What can I tell you? That's the kind of people we have out there. And the dangerous part, the surprising for me, is that I think there's more than 1% people out there that believe all this nonsense. I think it's maybe closer to 20%, and maybe I'm being too conservative. Okay, let's move on to dark matter. And what did I say? I think the mathematicians are full of dark matter. Okay, that's what I really think. Okay, okay. So what do we have here? What is dark matter? Well, dark matter is dark. And I showed you what it looked like. It looked like, black, okay, the other day. And it looks like that, what's underneath the green letters, okay? But I call it the dark matter conundrum. Okay, I think mathematicians have this conundrum. What is this problem? Well, it starts here, okay? So let's go slowly so that you see if you can follow along. Okay, so what is it? Let me get this in here. They put centripetal force equal to gravitational force. So we have centrifugal, towards the center of the galaxy, and centripetal going out to the flying away from the galaxy. And you have all these stars going around the galaxy, and they're pulled into the center of the galaxy by something called gravity. We don't know what gravity is, but somehow these stars are pulled. I hate to use the word pull because that already shows bias, but I have to use the word pull because everybody calls gravity a pull. I think ever since the days of Newton, everybody calls it a pull and then uses particles to prove pull. A little contradiction there. Anyways, centrifugal, we'll call it gravity, pull. And then we have centripetal force, which is, you swing the ball around, right? And this thing tends to push outwards. The only thing keeping it towards me, right, is the string. Other than that, the ball, if it's swung around, it wants to leave and go to another, out of the solar system. Okay, so what happens? The problem is they put centripetal force equal to gravitational force. That's a mathematical, almost a routine thing that they do. And it's deadly wrong. Dead wrong for the purposes of physics. This makes no sense in physics. In mathematics, mathematics could be. Mathematics, for sure. Physics, never. Okay, so let's find out why. Why you can't put those two equal. What happens is it starts here. They put force, Newton's second law, right? Force equals mass times acceleration equal to the gravitational equation. This is a no-no in physics. You can't get away with doing this in physics. That's the problem, okay? You can't do this in physics. Okay, so let's show why you can't do this in physics. Give me a second here. Here you have Newton's second law is mass times acceleration. Okay, and the gravitational equation is the gravitational constant g. It's a constant, so we can almost forget about it. We're going to talk about the other stuff there. Mass, big mass, little mass over r squared. What is r squared? Again, they should never use r. It's called distance, okay, not r. And that's part of the problem. The fact that they use r should never be used, should be distance. Okay, so that's the first thing I'm going to clarify. Okay, and we'll find out why. Okay, and so what's the issue here? Well, the issue is that the equation on the left, mass times acceleration, has to do with distance traveled. What the guy is doing there, with the little guy there, right? He's pushing the box. Okay, he's pushing a box, and what the mathematicians are going to do, they're going to look at his starting point and his ending point, and they're going to say, well, how many meters, how many kilometers, how many miles? They want a number followed by units. Okay, that's what mathematics does, and mathematical physics uses the same equation, the same notion. They say, well, we don't care about the qualitative part, the fact that he pushed a box. We want to know how many meters, how long was the trip, okay? That's not what the gravitational equation is about. The gravitational equation, like the guys say, their little r radius, which is wrong. It should be distance, okay? And again, you can't use radius because the Earth, compared to the moon, its radius, the orbit of the moon, for those of you who believe that the moon goes around the Earth, it changes. It's elliptical and so on. So you can't use radius because when you use radius, you're treating it as a circle. It's not a circle. You should use distance, okay? Because that equation gives you a single point. For that single point, you just look at that distance, okay? Not radius. And again, radius changes. And radius, the other problem with radius is that radius is calculated in meters and so on. And that's the other part of the problem. We're not going to be using units here. We're not going to be using numbers for anything, okay? We're going to look at this qualitatively. And we're saying that that equation on the left has to do with pushing, usually, right? Pushing a box from A to B. The other one has to do with the distance between A and B. And the mathematicians could never tell in the last 400 years, not a single mathematician picked up on this, that the distance, the separation between A and B is not the same thing as traveling from A to B. Why did they figure that out? Because in the religion of mathematics, distance, length, and distance traveled are synonyms. They don't care. They don't care about the qualitative difference between length and distance or distance traveled, because all they care is about a number. And the way they determine that number is by unrolling the measuring tape from A to B. No matter if it's separation, if it's distance traveled, or distance or length, right? They don't care. Because what they're going to do for distance, for length, for distance traveled is unroll the tip of the measuring tape, and they're going to count how many meters, how many kilometers, how many miles, or whatever. Okay, so this is the issue. Okay, so qualitatively, they're not the same, not in physics. So to put those two equations, one equal to another, they're comparing apples and oranges. Okay, let me get rid of this guy. So here we have the equation that mass times acceleration ends up being velocity squared over r, okay, for any star that goes around. I'm not going to derive it. You can very quickly look up on Google with at least high school level math, you can figure that out, okay? But acceleration is velocity squared over r, over the radius, okay? Okay, so again, we're saying those two equations are not the same. Let me get rid of this. Okay, so what's the issue with the stars? Okay, this is the issue. Here we have the equation that they come out of these two equations, right? One dynamic, which is the one on the left, the other one static, the one that's on the right, okay? And from that, they derive the equation at the bottom, which is the velocity squared is equal to the gravitational constant g. Again, it's a constant. We can almost omit that for the purposes of our discussion. We don't care about that if it's going to be a constant. We're concerned about the big M and the little r. What's the big M? Well, the big M is a big mass, for example, the sun, and the little m would be the Earth. Or the big M would be the Earth, and the little m would be the moon. And the same thing happens with a star. The galaxy, or the you can say the perimeter, the orbit of a given star, anything within that orbit, all the mass that you find in there, all the stars, that's going to be the big M, meaning the galaxy. So that would represent the mass of the galaxy. And the star that's on the outside going around the galaxy, that would be the little m, okay? What is the r? It's the distance between the center of the galaxy and the star, okay? And what they're saying is that velocity of that star going around the galaxy is related, the square of the velocity. We don't care about the square because we're interested in the qualitative aspects here. But yeah, the square of the velocity of that star going around the galaxy is equal to a ratio of big mass, in this case the galaxy, over the radius of the star, from the distance of the star from the center of the galaxy. Okay, so that's the story. Okay, now what's the problem with that? Well, it creates some problems for these people because here you have the situation. Okay, give me a second here. Okay, and what is it? Again, we have distance traveled is what you have embodied in that little velocity. Okay, that's what we have. That's the distance traveled. Okay, and what do you have in the other side? Well, you have something different. You have distance, meaning separation. Okay, that's what we have there. Okay, so I want you to keep that in mind. Okay, and here we have a galaxy. Okay, and so what are we talking about? We're saying that there you have the radius of that star to the center of the galaxy. Okay, that's that little r there. Okay, and here we have another galaxy. Let me get it up here. And it's got a bigger radius, as you can see there. Okay, so one is a short radius, the other one is a long radius. That's what I'm showing there. Okay, so what happens? If the radius increases, okay, we're going to increase the radius, okay, that radius there, okay. If the radius increases, then you can see what it's going to do to the velocity. As the denominator becomes bigger and bigger, that velocity, what's going to happen to it? Well, it's become smaller and smaller. Okay, so the velocity of the stars on the outside should be slower and slower and slower. Okay, the farther you are, the longer the radius or the longer the distance between the center and the outside of the galaxy, velocity should be slower. That's what I'm showing there, okay? That's the point that I'm trying to make there. Okay, and so what's the problem with that? Well, the problem is that the chart that they built from observations of galaxies looks more like this. That the farther you are, instead of going slower, which is the expected there from the visible disk, instead of going slower, it goes faster, or if anything, stays more or less the same. But never does it go slower. And you say, how can that possibly be? It violates the equation. Okay, the equation said that the farther out you are, the longer the distance, the longer the radius, okay, from the center of the galaxy to a star, the slower it should go. And it should, so velocity should drop as a function of distance, okay? And that's not what we see out there, okay? So this is the problem. And so they had to address this problem because they saw it in all the galaxies. And you say, hold it, all the galaxies? How do we solve this problem? Okay, and mathematicians, you know, they came to the rescue. They always save the day, okay? And so here we have our equation again. Let me show it to you. Let's start here again. Okay, there we have the equation, our two galaxies, okay? And so what happens when we increase the radius? Okay, we're going to increase that radius, okay? And there we go. Let's make it bigger. Whoop, okay? And so now we have a bigger radius. Okay, so what happens? Well, velocity should shrink, okay? So how did they fix this problem? Well, this is where the funny part comes, okay? What they did was they started putting some things in there, okay? They started putting some mass. They said, what if we put more mass to compensate for the longer radius? Okay, so that way they can keep it constant, or if you put even more mass, you can even get it to go faster. So what they said is, we're missing some mass. That's all that the problem is. That's the only way they could think of that they could fix this. Okay, so they said, let's put some more mass. And what they said, but we don't see any mass there. Okay, so it must be dark. And they called it dark matter. Okay, so they say, okay, now I understand. There's mass out there. You know, I can't see it, so we'll call it dark mass. And better yet, let's call it dark matter because it's got to be some kind of matter. Remember, matter is mass, matter has mass, or matter has mass. Okay, so what they did is essentially this. They sprinkled this dark matter on the outside of the galaxies to produce the necessary mass, okay, the mass that they needed for the equation to come out right. This is all about equations. Okay, and so here you see the chart now. Yeah, if you sprinkle a lot of kilograms out there, only out there, not inside the galaxy, then yeah, you can produce the result. It's like, you know, this fixes the problem, doesn't it? You know, we can't see the stuff that's out there, but if we sprinkle these kilograms out there, okay, then obviously, you can produce the effect, the necessary effect that matches what we observe. The equations now match what we observe, and we're just going to call it dark matter. And so what they did after that was say, okay, so we have our dark matter. Now what we do is we look for it. So now they have the dark matter. They proved dark matter. They couldn't think of any other reason why the stars on the outside would go faster than the ones on the inside. So they said, okay, it's got to have a mass. What else could it be? That's the type of answers the mathematicians give you. A star rolls around nothing. What else could it be except a black hole, right? A lot of mass in the center, and the star is rolling around this inexistent singularity. What is dark matter? Same thing. We don't know why the stars on the outside go faster. Very easy solution. Let's sprinkle some mass there on the outside of the galaxy. I don't know why this dark matter is only on the outside of a galaxy, but that's where it's at. Why? Because that's where they need it in order for observations to match the equations, or for the equations to match the observation. So they have here the observation. They say, this is what we observe. How do we fix it with our equations? Very simple. Let's put some mass in there. And they called it dark matter. So dark matter is an equation. They've never seen it. And they already confessed that. They said, we've never seen dark matter. So they don't see dark matter. It's not really dark. It's invisible. It's more than invisible. It's translucent. You can see right through it. Transparent, translucent. You can see right through it, because we can see stars in the background right through the edge of a galaxy. And so you say, well, hold it. With all these galaxies behind it, we can't see it even. I mean, if it's dark and suddenly, you have the disk of a galaxy, suddenly, with another galaxy in the background, or stars in the background, that you should be able to see the dark matter. Say, oh, there's the dark matter. Like, when you see Mercury or Venus go across the sun, it looks like a little dark ball. Well, this is what you would see if you're looking at the edge of a galaxy, since all galaxies have dark matter on the outside, right? So anyone that you look at, you should be able to see the dark matter. All we have to see is some kind of star or some kind of galaxy in the background that kind of puts a little contrast there. We should be able to see all those little stars, all those little balls of dark matter, just painting the outside of a galaxy. We should be able to see it. And they haven't seen it yet. None of it, okay? So what happens? They gave the task to the accelerators, to the LHC, and to all these other accelerators. They're looking for all this stuff. And here you see what the LHC tells us, the CERN, the people who do accelerations here in Switzerland. And what they do, they accelerate particles, or so they think they do, and they smash them. And from accelerating and smashing them, they purport to explain dark matter. They expect to find dark matter and explain how our universe works out there, okay? So we're going to figure out what happens out there in the galaxy by accelerating particles here, in the accelerators. And what's the issue there? Well, the issue there is that, remember, dark matter weighs a lot. They say a little grain of dark matter weighs tons. And there's lots of that out there, because you need lots of it out there to make sure that the star travels fast around the galaxy, right? So they have to sprinkle a lot of this stuff. Now they want to find those grains of sand in the accelerators. And so here's the LHC. This is what they say: breaking new ground in research for dark matter. So now dark matter has entered the accelerators. The Large Hadron Collider, LHC, is renowned for the hunt for and discovery of the Higgs boson. But in the 10 years since the machine collided protons at an energy higher than previously achieved at a particle accelerator, researchers have been using it to try to hunt down an equally exciting particle. Remember, this is a particle, a hypothetical particle that may make up an invisible form of matter called dark matter, which is 5 times more prevalent than ordinary matter, and without which there would be no universe as we know it. So if dark matter collapses, if that religion, falls down the drain, well, then we wouldn't have a universe. Okay, so dark matter had better be true. Otherwise, all the theories about how our universe works, disintegrating overnight. The LHC dark matter searches have so far come up empty-handed, as have non-collider searches, but the incredible work and skill put by the LHC researchers into finding it has led them to narrow down many of the regions where the particle may lie hidden, necessary milestones on the path to a discovery. Okay, so they continue with this. It's important to hear what these people have to say. The LHC has really broken new ground in the search for dark matter in the form of what? Weakly interacting massive particles. Why? Because they say that this dark matter weighs a lot, is invisible, but does not interact with matter. And we're saying, hold it, we got a problem. What do you mean it doesn't interact with matter? If it doesn't interact with matter, how is it that it affects the speed of stars? I mean, if it doesn't interact with a star, why would it push a star to go faster? That's the issue. If it's not interacting with matter, what's the point of having this heavy, invisible particle out there that doesn't interact with anything? Yeah, what does it interact with then? But continuing here, it says, by covering a wide array of potential signals predicted by either production of dark matter or production of the particles mediating its interactions with ordinary matter. So this stuff is not ordinary matter. It's very heavy, it's invisible, but it doesn't interact with matter. Great. I hope they can find it. It sounds like they're talking about a ghost. That's what I think they're talking about, spirits. The results have prompted theorists to rethink existing ideas for what dark matter could be. Yeah, I mean, what is it? I mean, does it have shape? This dark matter, does it look like a ball? What are these people, can they draw dark matter? What are we talking about? A bunch of balls, little balls there, little beads? Heavy, no, obviously. To look for dark matter, the LHC has been trying to make it by colliding beams of protons. Some experiments are using telescopes in space and on the ground to look for indirect signals of dark matter particles as they collide and break themselves out in space. Oh yeah, good luck with that one. They're looking for ghosts that are hitting each other, right? They're going to crash against each other. Maybe, I hope they don't go through each other, because if they're translucent, if they're invisible, they're dark but invisible, right? Or again, translucent. If they're very heavy, but they don't interact with matter, maybe they might even go through each other, and you'll never see them collide, right? I mean, why would they collide? Others still are chasing these elusive particles. Absolutely, they're chasing them, right? Directly by searching for the kicks or shakes they give to atomic nuclei in underground detectors. The main signature of the presence of a dark matter particle in such collisions is the so-called missing transverse momentum. To look for this signature, researchers add up the momenta of the particles that the LHC detectors can see. More precisely, the momenta at right angles to the colliding beams of protons, and identify any missing momentum needed to reach the total momentum before the collision. If the total momentum after the collision is not zero, the missing momentum needed to make it zero could have been carried away by an undetected dark matter particle. Yeah, it could have been carried away by an angel also. I mean, I don't know what these people are doing, and you're paying for it. This is paid for, by tax dollars, because if the tax dollars of the U.S., for example, don't go to CERN or LAC, it still goes to SLAC and Fermilab and Brookhaven and all these other colliders, and they're doing the same thing. So yeah, your tax dollars are paying for this nonsense. These people are looking for ghosts. They defined it as a ghost. It doesn't interact with matter. Sounds like a ghost. The ghost, as far as I know, doesn't interact with my curtain. Some people say it does, but these people are saying it doesn't. It's very heavy. It's very invisible, very translucent or transparent. And so what are we talking about? It looks like we're talking about a ghost. This is a phantom they're looking. And of course, when you're looking for a phantom, it's very hard to look for it with a telescope or by smashing them. Because again, if you smash a ghost against another ghost, and they're both transparent, translucent, maybe very heavy, but they don't interact with matter, maybe they don't even interact with each other. I think, Casper would go right through one of the other ghosts without any problem. So I don't know. I don't know what these people are looking for with your tax dollars, okay? Okay, so here we have, this is what the LHC does. It accelerates particles, okay? down the beamline, and they're gonna send them all around, the lengthy accelerator there, and they're gonna make them collide at some point. So this is where they plan to find the so-called dark matter particles. Here's the collision. Okay, so you go in there, you smash two of these dark matter particles, I guess, or they can smash protons. I guess they're going to produce the heaviness of a dark matter by smashing protons against each other. I have no idea what they're trying to do here, because if they're going to smash, for example, protons as they've been doing to try to get a particle that's out there in space which weighs tons, I'm not sure you can do it with a proton which doesn't weigh as much. Unless maybe they say, well, it depends on the energy with which we accelerate them. Okay, and yeah, if the notion there is that energy has to do with mass. It's another form of mass. If you put enough energy in the gazillions of whatever units, keV, okay, or gazillions of electron volts, yeah, if you smash two of these particles at great speeds, which is what they're talking about, maybe they can produce the weight, the mass of one of these dark matter particles. And when they smash them, they're going to tell you, look, it looks like that. Because I'm sure they're going to find it. And they're going to say, look, there we smashed two of these particles, and this is what we got. And they're going to say, see all those? Those are, each one of those little guys out there, those are the dark matter particles rushing away from ground zero. So this is the way they're going to handle it. Believe me, these people are going to find, without any doubt, they're going to find dark matter, or their name is not Albert Einstein. Okay, so yeah, they can't fail. Okay, it's too big to fail. Okay, how do we do it in science? All this dark matter stuff. Well, it's very simple, and I hate to put it because it's just going to embarrass these people later on when they see it. I mean, they made a monster out of this whole thing, a mountain out of a molehill. Okay, here's oh, by the way, this is just a comment by a guy at the LAC. He says, dark sector scenarios, meaning dark matter, right? This studying that they're doing, all these evaluations, provide a new set of experimental signatures, and this is a new playground for LHC physicists. Yeah, you're paying for these people to play. They've got all these games that they're playing out there. They're trying to accelerate protons at great energies. It doesn't accelerate the speed, but for some reason it imbues a lot of mass to the protons when they smash them. I guess some particle comes out there that is heavy enough to be called a dark matter particle. And they say, we found it. Here it is. They bring it to you. Here's the dark matter where we found it. I know, sorry, it's got to be dark. It's got to be more like this. Okay. Anyways, how do we handle this in science? Again, real physics, genuine physics. Okay, so here it goes. Again, I hate to embarrass these people, but here it is. Okay, we're saying all stars are physically interconnected. We don't pay attention to mass. We don't pay attention to equations. We don't care about those. We just say that if all stars are physically interconnected, we have a physical mechanism, first of all, for why stars are not flung out of the galaxy. That's the first issue. The second one is that, stars on the outside, you can see why they would go either faster or at least at the same speed as the ones on the inside, because the whole thing rotates like a carousel. That's why. Okay, the whole thing spins around as if it were made of a single piece. Okay, because they're all interconnected if all atoms in the universe are interconnected. Okay, so that's the first issue. And just in case, we reinforce this by showing the galactic magnetic field. Okay, here it is. So not only does a galaxy spiral around, but it's perpendicular to it. We have the magnetic field of the galaxy. Okay, and very easily to imagine that these magnetic fields, they have to stretch, incredible amounts of distances. Imagine the magnetic field of the sun stretches beyond Pluto. And people say, how can a magnetic field go that far out? And yeah, and it does. It's already been measured and so on. So the magnetic field of our star actually protects us from, interstellar influences of all kinds. And it's very likely that if you put several of these galaxies, one with respect to another, their magnetic fields probably interact. And where they do, maybe we can see some fancy things going on, like maybe you get black holes because you have all these galaxies, all these with strong magnetic fields, and where all these magnetic fields meet, there should be some interesting phenomena going on to stars that are caught in that region. Okay, because we're talking about magnetic fields. What are they? They're threads that are swinging around the galaxy and hitting essentially or sweeping by stars. And remember, a star, has electricity and magnetism. Those magnetic fields that you see in the sun. What is that? It means that there's some electricity going on inside or at least in the surface of the sun, producing those magnetic fields. So we have electricity and magnetism, and here you have the magnetic field of threads, right, of the entire galaxy sweeping down on this little charged ball. And yeah, it's going to swing it around. It's going to do things to it. And so, yeah, we have to look at this in physical terms, and the physical terms are threads. That's what physical is. When you use words such as mass and field and energy, you're not talking about physical entities. So you cannot explain how the universe works, the workings of the universe, gravity, electricity, magnetism, right? You cannot explain it with concepts. You gotta use physical objects. You gotta identify the invisible, intangible physical objects that are out there. And in the case of dark matter, very simple. Dark matter simply is an inexistent equation. It's an equation for inexistent objects, things that are out there. What are out there is that all atoms are interconnected, and that means all stars are interconnected. That's the reason stars don't fly out of a galaxy. They're not flung out of the galaxy when the galaxy spins around. If you add to that the magnetic field of the galaxy, it maintains the integrity, or helps to maintain the integrity of the whole galaxy. And that explains why, all these galaxies don't break apart, and you see them as, when you see these up close pictures of these galaxies, what you see is gazillions of stars just twirling around the center. That's what a galaxy is. What you don't see are the ropes that interconnect every one of their atoms, and you don't see the galactic magnetic field, even though even the mathematicians accept that there is a magnetic field. They just don't pay any attention to it. Okay, they never factor the magnetic field in anything of a galaxy. Okay, let's move on to a couple questions we had aside from the ones from the Moonies. Okay, one fellow says, I guess he says what science is supposed to say, and I think he said them all right. He says, science says fields are just mathematical concepts. Absolutely. Electricity is conceptual. Yes. Energy hasn't been defined. You get it right on the nose, right? Experiment, observations, math isn't a part of the science physics. Exactly. Weight and mass are the same measures. Yeah, according to mathematical physics, weight and mass are exactly the same because they've never been able to separate mass from weight or weight from mass. They weigh both of them, and then they tell you that mass changed, that weight changed when you went to the moon, but the mass did not. Well, how did you determine mass? Well, we weighed it. Okay, so yeah, mass and weight are the same. And light doesn't slow down through a medium. Exactly. You got them all right. Good. You get 100 points on the test. Okay, good. Now the fellow says, theory of stellar metamorphosis I find really fascinating. Jeffrey seems mentally ill. He's talking about Jeffrey Walensky, okay? Pretty sure Bill is annoyed at Jeffrey for tricking him into thinking the stellar metamorphosis was Jeff's idea, so it's only been covered once on Bill's channel. Oparin, I think, was the first. Yeah, Alexander Oparin, 1920s. He wrote a paper. He wrote also a book on that, and he's the guy who really comes up with the so-called stellar metamorphosis theory. I think that title comes from Walensky, not from Oparin. I don't think Oparin gave it a name. I read the paper. I don't remember him giving it a name. He just explained the process, and he says, "Yeah, look, what this is that that all these planets were made essentially by they were stars. At some point, they were stars, and I like the theory, and I like it for two reasons. I always say that. I like it for two reasons. One is that it shows why all celestial objects, or almost all of them, I mean the big ones, yeah, they're all round. They're all spherical, except for flat earthers. There's some flat plates floating around, but I try not to look at those. No, all celestial objects, especially the big ones, they're all round. And so if the Earth is round and Mars is round and Pluto is round and Mercury is round, even the small guys, they're all round. Ceres, which is the smallest, well, it's the largest asteroid, but is also round. And then Mimas, one of the moons out there, which is the smallest object in the solar system, is also round. And lots of these are theorized to be differentiated, meaning that they have all these layers inside them. So they're round and they have layers inside them, the heavier ones on the inside and the lighter ones on the outside. What is that a description of? A star. All these objects were stars. They did not form like they say the nebular hypothesis that gases condensed. Among other reasons, because the moons of Jupiter, for example, why would they be rocky while Jupiter, which is next to them, is gaseous? Okay, there's no reason for that to happen. If Jupiter was made through gases that were around the sun, condensed gases, so should have all these little planets there. Why would they have metals, solid rock, silicon, etc., carbon? And here's Jupiter next to him, has the structure of a star, of a small star. Yeah, no, the sun, yeah, nebular hypothesis, no problem there. But all the other objects were that that our sun captured were already there. The sun, I'm saying, was the last one to ignite. It was this gas cloud that condensed, a big gas cloud condensed and captured all these objects into its orbit. That's what I see here. And again, what this theory, Oparin's theory, shows, at least to me, that's why I like it. It shows roundness and differentiation. As far as Walensky, well, yeah, I think I don't talk to him because I think the kid's got a problem. And I'm not trying to put him down. I'm just stating what I think is a fact. I think his loved ones should do something for him. I think this kid has some problems, some issues. And so, I think it's not worth talking to him, not because I hate him or anything. I don't want people to think that. I just think he's got some real issues. So yeah, I think he's got to be looked at. That's my take on him. Okay, and here's last one says your equation belief equal knowledge is false. Okay, I didn't create the equation. Okay, the equation was created by Mr. Plato, first of all, and it hasn't been improved on in the last 2,000 years, 2,400, I guess, more exact years. So, no, it was Plato who said, knowledge is justified through belief. Now, whether you believe that or know that, well, that's a separate issue. I'm just telling you what knowledge is out there, and you can't say, well, that ain't what is true. You got to say what is true. Okay, and this is one of the problems that all these people have. They never tell you what is, they tell you what ain't. What is ether? I say, well, it's a bunch of particles. They say, no, Bill, you're wrong. It's not, ether is not a bunch of particles. Okay, and and then the atom, all the little balls, they don't roll around the atom. Okay, that's not the atom, then what is the atom? And they never answer the question. Here this guy says, no, knowledge is not belief. Okay, so what is knowledge? So they never answer the question. They just tell you what it ain't. Okay, you forget observation. Yeah, we don't use observation in science. And he says, if you do not observe, how can you get factual knowledge? If you do not observe your pencil fall down from your hands, how you knowledge the fact that the pencil fall down to the table? Okay, I think we understand what he's saying. He's asking, here, let's do it here. Here's the pencil. Okay, he says, if I don't observe it, okay, here it goes. The pencil fell down. Let me do it one more time, okay, just in case. Okay. So if I let go, it goes down. Okay, fine. Now the question is, how can you talk about gravity? How can you even begin to explain something if you have not used your eyes first? And what can I say? Here's the answer. Here's a blind man. Okay, and the poor blind man is also quadriplegic. So he can't touch, he can't sense, he can't even move his hands, and he's blind. He's there, in his wheelchair, I guess. And someone comes to him and says, "Look, because he's a smart man. He's just, invalid. He's got handicaps, unfortunately. Yeah, but he's got a good mind." And so someone comes to him, and fortunately he can still hear, and whispers in his ear and he says, "Look, there's a pencil, and I let go of it and falls down. And I do it a million times and it does the same thing. It always falls to the ground, never falls to the ceiling." Well, the blind man, he hasn't seen anything. He hasn't touched anything. He's just got someone who might be telling him a lie for all he knows. He's telling him in his ear. And he says, well, let me give you a solution. What if every atom of the pencil is bound to every atom of the earth? That would explain why it falls to the earth and not to the vacuum of space. So he gives him an explanation without having seen or touched or run an experiment or done anything. In fact, he can put a hypothetical situation of the Klingons on the other side of the universe. So what if, right? What if a rock hit the moon over there on the other side of the universe? He hasn't seen it. He hasn't touched it. He just, what if? How would I explain it? So no, to theorize, you do not need to see, touch, or run any experiments or make any predictions or observe anything or none of those elements that the mathematical physicists have included in their version of science. With that, I'll see you on Sunday. We'll see you there. Bye.